All right. Yeah. Hello, everyone, and nice seeing you again. I was actually already here last year. Who has also been here last year and seen my other talk? Oh, I'm actually seeing 3 hands. That's good. Well, to those who don't know, who are just watching the recording, there is not too many people in the audience. Let's say maybe 25, but yeah, it's a good number. Anyway, yeah, I'm happy to be here again. I'm Daniel, as you already heard, and today I'm going to present on tools that I made and also other people made for working with chips. And by chips, we don't mean the things that you can eat, but what we have in our computers here. And yeah, because they are like everywhere nowadays, there are some opportunities for us to hack on them, or when we buy like single board computers, actually get down to working with them on a very, very low level, like before an operating system, and that's our main topic for today. So yeah, this is me. Yeah, I mostly actually professionally worked as a web developer, but I also did a lot of open source stuff in my free time. That was mainly then, around firmware and operating systems and all that sort of stuff. And yeah, over the years, I've now gained a bunch of experience, and yeah, I'm going to share a bit more on that today. And at some point, I created a tool that is called Fietka. It's a firmware editor, so it's like an app that you can use, and then you can load a firmware image and look at what is inside the image, and you can edit it to some degree. It's still some work in progress, so I'm not spending all my time on it, but sometimes I still get my hands on it. And yeah, feel free to also take a look at that. And otherwise, I created a project that is called Platform System Interface, which is now sort of turning into a large comprehensive documentation, which is like all around hardware platforms and operating systems and the interfaces in between. And we will actually get back to what we mean by systems, really, because it's not a clearly defined thing. So yeah, this is the rough summary for today. I will talk a bit about what systems are. I mean, most people here have seen chips, I guess, but I will talk about what really the what it means to have a system and a chip and so on. I will talk about the protocols that we can find in these chips and the so-called Masgrams. More on that today. And then I will present the implementations that we have so far for working with chips. So yeah, system and chips. If you want to know what a system actually is, you find like lots of different definitions, and that is because it's actually a very ubiquitous term. So we don't only use it in computer science, but it's also used in other places. It can also be politics, right? So there is like people who say, "Hey, fight the system" and stuff like that. That's not the kind of system we're talking about today, but it's in a very, very general sense going in that direction. So I looked at the definition on Wikipedia, and I thought, okay, let's find something that might be good enough for us here. So here's my definition for today. A system to us here now just be a set of components that is following a certain set of rules and acting like as a whole. So yeah, a system really just means you have something big and that consists of many different parts and they work together in a way. And that is what it looks like schematically nowadays. So when we design systems today, we create the so-called systems on a chip. That means that you have processing power, and you also have a bit of memory, and you have buses in between, and you have peripherals, and all of that is baked into one of these small chip packages that you find on the main board today. And they can be like all sorts of different things. We're actually happy now to have Abstrakt here. They make lots of interesting systems. If you want to look at them, go check out their stand. Anyway, I don't mean to advertise too much. So now the thing is, a system can also be something in a virtual sense, and that's what we then call an operating system. So an operating system is also something that consists of many different components. They work together in a way, they have interfaces and so on. And so, yeah, we just call that an operating system. But yeah, it can also be like a large range of different things. But in a general sense, that is also what we call a system. And yeah, if you follow this link here, by the way, you will get a link to the PDF later, so you can click on everything. You don't need to type it. I've actually, created an issue in my project to come up with a maybe more comprehensive definition, because yeah, it's really hard to define, I think. And the next thing I want to define here is what makes a platform, because a platform, if you have heard that term, can also mean many, many different things. People have started to talk about the so-called platform economies. Some people call Facebook a platform. Some people call something that is software a platform. If you have heard the term PC, it's a very old term by now. Some people understood that as a platform at some point. Sometimes they mean it's something that is coming with Windows installed. That would be a PC. So, you know, when you buy a game in a in a store, you can install it on your computer. Well, nowadays we don't buy CDs, we download them from Steam or something, but you get the idea, right? So you need to have the right platform so that you can run the software. And that is also the case here. So we can define a platform as a special chip with its own ISA, for example, the instruction set, and that also has certain interfaces, and you can also consider that a platform. If you look at the UFI definition, for example, so UFI is like an interface that we have in many of our systems today, they call something platform initialization. That is one of their large specifications, which is all about the system bring up right before the operating system. And that actually comprises lots of things. So yeah, in our case here, what we understand to be a platform is, well, a system with some interfaces, and that provides us an environment. So we know when we have a certain platform, we can run certain software on it, because, you know, it's like well defined in that sense. Yeah, I also put a little note here. So this is coming from my side here. It's not like the most general definition, but what I'm saying is the interface should be stable so that you can rely on that platform as being a platform. So if you take the literal sense of a platform, right, it's something that you can physically stand on. You don't just fall off, right? It's a stable thing. And I think that would also make sense to be a definition for a software platform, because it also means something you can rely on, that you can always run on. Like when you install software, you can rely on, it will actually run, because it says it supports this and that platform. All right. And now we're going to talk about specific kinds of systems in terms of hardware. Who has already heard about these terms before? Who has heard of an SoC? Oh, I see lots of hands. Who has heard of an SOM or some? Okay, I'm seeing a few less hands. So let's define those two things very quickly. So an SoC, or a system on a chip, that would be something, you know, that is now contained in these small plastic, or sometimes also other kinds of packages. So often you see these plastic things. And I've actually taken some pictures here so we can look at that. So what you see in here, this square-shaped thing, which here says D1, I hope you can read it more or less. That is what we call one of these packages. So the package is like the physical thing. And in that, we have that system, you know, just as I showed before. So what I showed schematically would be represented in here. And there can be other chips, of course, like this thing here, that would be a memory chip. We wouldn't necessarily call that a system on a chip, you know, because it's like a special purpose part only. And you might as well see this one down here and that one, right? So those are like, we rather call those peripherals. So they are like additional things that we add to our systems. So yeah, the central part is usually the SoC. And there are multiple form factors. So this one here, I think it's a bit hard to see because that would be underneath. So I think this is a BGA chip. So BGA means that you have, you know, lots of little balls underneath. So BGA is for ball grid array, and then you would use that to solder it to the board underneath. And that brings us to the next term, the system on a module. So what you see here, this red square-shaped thing, that is what we call a system on a module, because it's a module, so it has a connector. And you can add that to any other design. So if you look at it, you see these connectors here. And then you have this purple board, which gives you even more access to like certain peripherals. And that would be the pins that are exposed through the connectors. There are different form factors of those things. So we have two examples here right now. So you see this big thing. And down here we have a smaller one. They're actually based on the very same chip. But yeah, here you can see it's a very, very small thing, and then it sits on one of these boards. These boards also have various terms. They are often called so-called carrier boards. It doesn't necessarily have to be that sort of thing. It can also be that, you know, these modules can also be like part of a main board in a laptop, for example. There are also designs nowadays for that sort of stuff. Yeah, but it's mostly often called a carrier board because it carries the system on a module. Yeah, I've written down a few small factors here. You might have heard of CM or compute module. That is, for example, famous from Raspberry Pi. They made a sort of standardized form factor so that more people who create one of these carrier boards can design it so that you can fit in a system on a module. And that gives you, well, it's a module, right? So it gives you some modularity. So in theory, you can swap it out and, you know, use a different system on a module. All right, so now we have these systems here. But we want to look at what is actually underneath. So we're going now to look at how one of these things actually boots up. So we have two more terms here. Who knows what a ROM is? Seeing many hands, yep. So ROM, or read-only memory, that means it's a memory part that we can only read from. Sometimes it's not necessarily true, some can be cleared and then be written again, but in this sense here, we mean something that you can really only read. And then OS, who knows OS? Or, well, operating system, I think most people here have heard it, especially if you're a student, you've definitely heard it, I think. So an operating system, but then, as we defined earlier, is also a sort of system. And now if you think about it, we have this hardware, the system on a chip. So we start with a hardware. There is a ROM inside, and then we make it into a virtual system. That would be the operating system. And we can generalize this flow like this. So what you have within the chip is this storage part, which is like, you know, you cannot write to it. It's only ever being read. So that would be the so-called mask ROM. It's just called that because of, I think it's because of the processes all those things were made at some point. Nowadays, they are also often called boot ROM. So if you look at a manual from a chip vendor, you would often hear the term boot ROM. So this is where the very first code is running that will bring up your system. The next part then, and that is what I talked a bit more about last year, would be you would initialize the platform. That would then become more of a virtual platform. Then you would have a bootloader, and then eventually your operating system. Yeah, but in general, you would always need to do these four steps just because, you know, how the hardware that we have today is designed. So, yeah, I wrote this down here again. So what we have today, the typical SoCs, they would have this sort of code in this mask ROM. There's also other terms. I've added another one that is ZSBL or zero-stage bootloader. It just depends on who you ask. Like ZSBL, for example, is coming from RISC-V. That is a certain instruction set. They just wanted to have their own word for it. And this brings us to what we're actually going to focus on today. So we're going to talk a bit about the protocols that you can get from these mask ROMs. So if you think about it, when this thing starts your boot flow, it means that it has to read your code at some point. It will need to execute your code at some point. And the question is, how do you then provide your code? And there are various means and methods. And a very simple method is, and that is offered by many chips today, you can just load code over a serial connection or USB. So let's talk a bit about these protocols, because you need to understand that you know, they have like lots of different nuances. It's not like there is just one protocol and everybody uses it. That would be very simple. So yeah, let's see what the mask ROM actually looks like. So as I said, it's baked into a chip. And it's the initial code that actually runs on your processor or SoC that we have nowadays. And that's why we also call it a boot ROM. It is often mapped to memory, which means you can also read it from memory, and you can dump it to a file. And when you can dump it to a file, then you can also look at it and investigate it. Who of you knows what a disassembler is? And yeah, or who knows Ghidra or has used Ghidra even? Yeah, I'm seeing some hands. That is very good because it's one of the main tools I'm using nowadays to, actually understand these things. So yeah, if you don't want to get started with Ghidra already, one of the very first things that you can actually do when you have like a file from Maskram, you can start looking for strings first to, understand a bit and see what is in there. Because often when you boot up a chip, it already starts printing something that is then coming from the Maskram. And that means you can get a bit of a clue of, hey, if I'm seeing the string, it means this sort of code is executed, and you can start following that. There is now a few things that you need to keep in mind. So when you look at the code, it's not necessarily just a very linear flow, but it's actually conditional in many cases. So many chips support, booting from different sorts of peripherals, like it can be from an SD card, or it can be from a flash part somewhere, like a SPI flash, for example. And that means that, there needs to be code to, handle all of these different cases. And sometimes you can configure that, like by talking to the chip and tell it to boot from certain peripherals. That is then the so-called OTP configuration, or one-time programmable. So you would program that into the chip. Sometimes you can never change it back again. That's a bit unfortunate, so be careful with that stuff. Or it can be controlled by GPIO pins. Sometimes you would have little switches on the board, and that can control the boot flow. Here's just one example from something I looked at in Ghidra with a few friends at some hackathon that we made. And yeah, in this instance here, I added my annotations. This excerpt, for example, is copying part of the code that is actually from the ROM. I would just copy that over to memory. It's, I think, not necessary in this instance here, but yeah, it might be sometimes necessary, to set up something. Anyway, it's the vendor's code, so yeah, I don't mean to criticize it or something. I just found it a bit odd because I'd never seen it before. Right, so why should we now actually bother with all of this stuff? Because it's like pretty complicated actually. And well, here is my pledge again. So we have these many single board computers nowadays that, many people are buying, and then they are a bit stuck with like, okay, what do I do with this thing now? Some of them just use the vendor's operating system and they might be happy with it, but it's very, very often that people want to do more with that stuff. And then they look for like, hey, do we actually have upstream support in Linux? Do we have upstream support in U-boot? Can I run my own custom stuff on it? And well, I work on a project where we provide our own firmware, so I always want to run my own code. And it's also true for many consumer products that we can get. Like, many of them, they're just made at some point in time, and then nobody touches them again. You get no more support. So you might actually want to have your own system on that sort of stuff. That can, for example, be like a TV box or something, right? So you buy something, it has some very old Android on it, and at some point it sort of expires because you can't install more recent applications anymore or whatever. Stuff that happens. So yeah, or as in my case, you might want to develop your own software after all. So here's an example. This here is a car media player. Well, you don't see the front part, but, that's what's inside. So in the front, you would have a display and you would have a knob to turn. And I saw, hey, there is a USB port. And when there is a USB port, I think, hey, that is connected to a chip somewhere behind it. And I actually took a look into that thing. And I found something that is very familiar to me this year. So yeah, this is from the same chip vendor actually as what I showed you on the pictures earlier. In this case, it's Allwinner. And I know they have a nice protocol that I can work with if I only figure out, how to get in a certain mode so that I can talk to this thing. And what I did here is I connected two probes to the flash chip here. And then I connected them when the chip was booting up. I was effectively grounding one of the pins that would be for data communication so that it couldn't actually communicate with the chip properly anymore. So it couldn't load any data. And what that chip would then do is it would fall back into a loader mode. And now I could connect something to, so I could connect a USB cable to the front port of that thing. That would usually be for, playing MP3s from a USB drive, but I can also connect it to my laptop. And now I can actually put my own code in that from my laptop. Well, or download the code that is on the flash chip here, when I release the pins again. So yeah, now just a few notes if you want to do this sort of stuff, just so that you are prepared. So when you just, you look at some random hardware, you might actually need to do a bit of research. So here's a few hints. So first up, as I already said earlier, many vendors, they have, their own protocol. So like if you look at a certain chip, first check out what the vendor is. Can be anything. It can be Espressif, for example. It can be Qualcomm. It can be MediaTek. Any sort of chip vendor. And usually there is people who already founded a community around that stuff, and they would then already have had a look at that, or you might be the first ones. If you're the first ones, you're a bit unlucky. But here is now the next steps you can do to figure out a bit more. So you would often have a protocol, but you would usually not have any documentation. So if you look at the vendor's website, usually you wouldn't find like, hey, this is our Mascrom protocol and this is how you can work with it. That is very unfortunate. So the next thing is we can see, hey, do they actually have something on GitHub? So do they already have their own code? If that is the case, then we can look at the code and you can get an understanding through that way. So when for example, actually, I'm going to show a few demos a bit later. When I bought a bunch of machines myself, I actually looked at GitHub and then saw what the vendor is doing with their code. And sometimes you can get some ideas. Maybe you can also do a bit more. Well, if you are very unfortunate, it might only be binaries. Then you would resort to Ghidra again and start reverse engineering the stuff. Maybe again starting with strings. Then if you connect to a serial port that you may find on a given mainboard or your system on a chip or whatever, it depends a bit on the board design, but you can often find a serial port and then you can see if you get any output from that. It might tell you something about the machine state. For example, some chips, they would just print some early message and say, hey, I'm configured this way, and then starts your system. Sometimes, as I just proposed earlier, when you already have a dump of the Mascrom, you can also analyze that one and gain some more understanding from that. And sometimes, it might be hard for you to get your hands on a Mascrom yourself, but it might be that somebody else has already done it. They just, I don't know, dumped it on GitHub maybe, but they didn't proceed any further, and maybe you might want to take it a bit further. So yeah, always good to check out what's on GitHub or GitLab or Codeberg, any of these platforms. I've also seen that sometimes there are hidden commands. So even if you have like a vendor tool, it's already quite nice. It has its certain commands. You try to play with it. It might actually be that there is more commands in there that are not documented if you type, I don't know, the command and then -- help or something. So it can be that it gives you some idea of, hey, I can also try this out. So we found that in one vendor's tool, for example, when we just looked at the strings that were in the tool. So we found the commands that were also presented in the help, and then we found something that looked like additional commands. So we just tried them out and they worked. Yeah, and the last thing I always want to put in here, because it can be very easily breaking your chip. So you also find something on many chips nowadays that is called OTP, or one-time programmable storages, or sometimes they are called fuses or eFuses. So there are some bits in the chip that you can only set once, and then they are set forever, and you can never change them back. And that means if you mess them up, it might be that you log out yourself from the system. It can also be that you buy a product and that already has those fuses set, and then you cannot change anything yourself. That is, for example, what we have on many platforms nowadays in our laptops, so that you cannot tamper with the system. All right, so yeah, let me now present you with a few implementations that we created. And I will start with one that we've already done quite a while ago. There is a chip vendor that is called Star5, and they were one of the first who were making RISC-V chips. So Allwinner was actually the first one I got chips from, and then came Star5 at some point, and now we have a bunch more. And well, what they created, I just made this tiny little table here for each of the tools. So they're using the UART interface, so that's like a serial port, and then they have a protocol on it. And when I looked at that, I actually learned, hey, that protocol actually has a name, and it's quite an old protocol. I think it's from the 70s or something, and somebody just created that for, just transferring files between two computers back then. It was, just very messy, very ad hoc. They just created it for that one purpose, but it somehow evolved further, and people are still using it today. Quite funny. There is just a problem, so the implementation here was a bit quirky, and that's why we couldn't just use a generic Xmodem tool, but we had to work around a few things. To be honest, I'm not even sure what the exact quirks are. We just got it to work somehow, and yeah, I followed somebody else's implementation for that. Yeah, in this case, you cannot actually interface much more with the chip. So what you can do with that is you can just transfer your code over to the chip, and then it would just start executing your code. And that's it. But that's usually good enough. So when you can already execute your own code, you can continue from there, right? During development with this thing, I actually did a few live streams. They are now archived on YouTube, so you can look at that with this playlist here. All right, so another thing I looked at was Mlogic. If you don't know them, they make lots of chips that are used, for example, in TV boxes and also some other systems sometimes, and they would then commonly be running Android or something, right? But Android is on a very high level, and before that comes all of like the platform initialization and then bringing up a Linux kernel at some point and so on. But they don't only make TV boxes, so there is also vendors who would make certain development boards. If you know the Raspberry Pi boards, there is also other fruit boards that you can get, and they some of them actually come with Mlogic chips. So we need tools for them. So I figured Mlogic is using the USB port usually, and they have their own proprietary protocol. Unfortunately, at some point they also switched around a bit. Nowadays, you can also use fastboot with those chips. That is very nice, but it also means that you need to look at the specific chips to figure out what you can actually do with them. I'm not exactly sure though, so I just figured that, sometimes chips allow you to do this or that thing. It can be because of OTP configuration. I'm not certain. So yeah, if you want to check out more, yeah, go and look at this tool here. We call it AML boot. And yeah, down here you find a small video of something where I just created a tiny program that it would just make an LED blink on a board. Right. Another vendor I looked at, and that is what we're going to see a demo on in a bit, is Kendryte, or Canaan. So Canaan is the vendor, and Kendryte is like a chip family from them. So they also use the USB interface, and they also have a proprietary protocol. It took me a while to figure it out, but on their GitHub I actually found their code for interfacing with the chip. I took that and then I extended it a bit, or fully actually re-implemented that stuff myself. And now we have a very nice and easy tool to just say, hey, there's a chip here, I want to run my code on it. This protocol here is also rather simple, so all you can do here is you can load some code and then run it. It's not very much, but yeah, as I said earlier, it's usually good enough, because as soon as you can run your own code, you can always provide any extra functionality you want. So the tool that we can then use, I will show that in a bit. You would then say, hey, I want to load code, and you also give it the memory address where you want to load the code. Which means if we can do this more and more often, we can actually go in multiple steps. So we can run some first code, we can jump back to the master, and then we can load some other code, and we can populate the whole memory with as much data as we want, or code actually. Yeah, again, also here I started creating a little playlist, where we were hacking on this thing. And that gets us to the first demo. So yeah, I have one of the boards here. There is nothing much to see here actually, because I have it in a very nice case. You can take a look at it later if you like, or I can also show you something later on the internet maybe. Anyway, so what I'm now going to do is I am going to run some code on this. So first I'm going to connect it here. And I actually have two USB connections to this now. So one is to connect to one USB port. On that USB port, we have the Maslowski's protocol exposed. And on the other USB port, we have a serial connection. And what you see down here is where my cursor is. This is where you get the serial output then, because I already opened a serial connection to this. So yeah, I'm going to run something now. This is from our firmware project, and what we're going to do is 3 steps. The first thing is we're going to load some code that would then be running, and that first code would print something, and then we will jump back to the Maslowski. In the next step, we will load some extra code, and that will be a Linux kernel. I will load that into the DRAM, so in the larger memory, and that's what I initialize in the first part of code. And then I will run another bit of code, and that bit of code would then, set up an environment for Linux to run, and then Linux has a platform, and if all goes well, we just see a Linux kernel running in a few seconds. So yeah, this is our initial code here. You see this here, boot failed. That is actually coming from the Maslowski, so, the Maslowski would always print that message when it doesn't find anything to run. Anyway, so yeah, as promised, it already worked. So yeah, here we have Linux, and we just booted it in 3 seconds or something. And we didn't need to have any SD card or storage or anything. It was just all over USB. So yeah, as you know, Linux, we can now say, I don't know, uname, for example, right? So you have my kernel version here and so on. Yeah, I put my nickname in here. And as you can see, it's actually a rather recent one. So this is from like end of February. All right. And with that, we're heading over to the next chip. And the next chip is from Buffalo Lab. You might probably not have heard of those people yet. But yeah, there is actually a bunch of products maybe in the makings. I'm not sure how this will work out, but I saw they have like partnerships with lots of big cloud vendors like Amazon or Google or something. So yeah, they might be creating something to be integrated with like the Amazon Alexa stuff or Google Home, whatever. But there is also a few other people who are designing stuff with their chips. For example, Pine64, if you know them, they also make lots of single board computers. Yeah, they are also offering some boards with a chip called BL808. And that is also what I got my hands on. Yeah, this here is now a slightly different board. It's from another vendor called Cypete. But nevertheless, so I'm just using this here for development. And what you can do on this thing, it actually has a very, very rich interface. It's also a proprietary protocol. This time it's not USB, it's now UART, so it's a serial connection, but it runs at a very, very high baud rate. And high baud rate means you can also, do very quick transfers. Otherwise, serial can be very, very slow. So if you run at a low baud rate, that's actually what many chips do, then, it might take a long while if you want to run some certain code. I also found they have like, lots of configuration in their OTP fuses. And so what I did was I looked at the vendor's code implementation again. And then I created my own tool based on that, and also based on a lot of knowledge that I could gather from the community. So I figured, some people already, got started with that stuff also a few years ago. And yeah, they created this project called Open Buffalo. And yeah, I also created a small playlist with that thing already. We haven't done yet very much. I think it's only 2 videos. But yeah, again, you see this playlist on YouTube. And with that, we're heading over to the next demo. And for that, I need to connect another USB cable again. So yeah, this here is actually similar to the other board. I have 2 USB ports here. And one of them is the port that is offering me 2 serial ports. So, and one of those serial ports is then actually what gets me in the Maslowski protocol. And now I just need to be sure to connect the right one. All right. And let's look at the tool. So that would be here. I just call it BL boot, as in Buffalo Lab boot. And I will quickly show you the options that you get with that tool. So as you can see, we have like a good bunch of commands already. One of them is very, very simple. There is a reset command. So the reset command, it's essentially just like when I press the reset button here, it would just jump back to the mask RAM. So I really just tell it to, hey, execute your code again. Okay. Then we can dump the flash. So there is a flash part on this board with like 16 megabytes of storage. There is also a board with 8 megabytes, but nevertheless, we can already use the mask RAM protocol to read out the flash part. So if you want to see what is already in there, for example, if you buy an eventual product, then you can take a look at that. And yeah, I've created a bunch of other commands. These here, for reading out the fuses, that is quite okay. This here for setting fuses, that is to be very, very careful with, because that's how you can break the thing very easily. So if you set the wrong fuses, it might be that it will never boot again. Yeah, then we have this command here, the run command. I just created that so that you can load and run your code again. That is usually the most common thing that I do. And then I started writing this command here, the flash image command that would then write to the flash part, and that would currently expect to already have a pre-built image. There is a work in progress to also build our own image. It's not yet fleshed out, so yeah, never mind that. We will get back to that at some point. And then there is a command called parse image, and that is because these images, they actually need to have like a lot of metadata in them. And that is very, very complicated to comprehend. And based on all the documentation I found in the community, I created this command that can then output all of that stuff. We're now going to look at a smaller set of information, and I'm going to just run the flash ID command. So this flash ID command here, I'm going to run an extended version on that. That will output the name of the flash part that we find, and then you will also see some additional information. All right. So yeah, here in the end, you see the flash part found. So we can see the manufacturer here is called Winbond, and the specific part ID is 1840. So these flash parts, they have like also an interface, and through that interface you can ask them, hey, what is your vendor, what is your product ID, and if you know that stuff, you know what special commands you can use for that thing. You can also know what the size of it is, and so on. And yeah, in this case here, Winbond is one of the main manufacturers. It's a well-known one. So you find a lot of information on that if you want to figure out more. But speaking of more, we actually have like a lot of information up here, and I just want to quickly walk through here, just give you an idea. So yeah, everything that you see printed here, it's really a lot of information, but if you read it out, you really just, you have a handful of bytes, and then you need to know what each of those bits or sequence of bits in there means. And as you can see, there is stuff in there like the Wi-Fi MAC address, even the package form factor, so you know what that chip actually looks like. It's a bit funny, so if you, I don't know, if you open up a box, you would actually see it yourself, but it can sometimes be that it's hidden, so this might be interesting at some point. It says flash none here. That is actually not really true, and I think that is due to some misconfiguration of the chip. Anyway, so it's not like the chip really knows what flash is there. It needs to have some information baked into the OTP fuses. And then you see like lots of these flags here. For example, boot ROM protection is on. I'm not exactly sure what that means, to be honest, because I can read out the boot ROM. There is a flag that is a very funny one. It's called UART log disable. That means I cannot read out the UART log. So usually, you would get some additional information by default. But there is this one. There is UART log reopen. So you can also set that thing. So you can disable the log and then you can enable it again. I don't know why they did that, but it made me giggle a bit. So yeah, and otherwise you see there is like lots of more information, and I'm not going to you know go further in the details here because there is so much, some of which I don't even understand myself yet, just because it's so much. Yeah, just if you see one of those chips, if you want to work with them, yeah, here is a tool that allows you to get like lots of information. And with that, we're heading over to the last example for today. That would be SoftGo. SoftGo is another chip vendor. They also make lots of RISC-V chips, so again, a reason for me to get them. And again, they have a proprietary protocol. It also works over the UART interface. So yeah, that also means a serial connection again. Theirs is not very fast. And it's also very sensitive. So the problem is, you know, when you talk to the chip and you use the wrong serial adapters or the unfortunate ones, you get lots of errors. And that was something, you know, that many people reported. I also had that issue. So yeah, if you want to work with the SoftGo chips, that would be the SG2000X series, like 2000 and 2002. There might be more coming soon. Yeah, be prepared for that. So you might need to find the right serial adapter. But yeah, there is a command in that protocol again, and that allows me again to load my own code. So we've created another tool for it. Yeah, this one is then called sgboot. So when you have some code, you can say sgboot run, and then that code will run. All right, and of course that's not where it ends. I already presented a similar list last year. There's like lots of other chip vendors. I haven't even put them all on the list here. So yeah, this is, you know, just to give you a rough idea. If you want to start hacking on certain chips, you might want to look at those tools here. You will find most of them just on GitHub, and you know there is also wikis where you get lots of more information. Yeah, and yeah. The thing is, because that already gets very, very messy, the folks from Android at some point, you know, they came actually up with a more generic protocol that most or many chips are now using. Not most of them, but many. That's usually what you find in your phones, like this one, for example. If you look for documentation, you would often find something that tells you to get into the fastboot mode, and fastboot is a more generic protocol. Yeah, it's defined in the Android protocol, in the Android repository. I also looked at that at some point. And there is also a Rust implementation for it now. So the original code is written in C, some was written in C++ at some point. Yeah, and some people created a Rust implementation. So if you want to understand that protocol a bit more, I would encourage you to take a look at that. And also the documentation. So we referenced that from our implementation, well, or the one that I forked from somebody else. I think they're not maintaining it anymore, so yeah, I'm doing that a bit now. And what's interesting about fastboot is it's not only in Maskroms, but it's also being ported to other platforms. So for example, people have taken the fastboot command and re-implemented that in fastboot, which means, in U-boot, sorry, which means if you want to, you know, have the fastboot protocol and you already have a U-boot port to a target chip, and that chip only gives you access to, you know, just run your own code, well, then you can run U-boot, you enter the fastboot mode, and then you can just use fastboot to, you know, do quick transfers. And fastboot runs, you know, usually over USB. And, you know, if you start with a serial connection that is very slow, and then you can switch to USB, it means you can, you know, quicken up your development. Qualcomm even did something funny. They put their implementation of fastboot into something called LK, or little kernel. It's yeah, another small operating system kernel that you can also find on GitHub actually. And then there is another tool that is called Snagboot. So Snagboot is essentially a collection to work with like lots of many different chips. I haven't taken a look into that in a while. I think it's written in Python, and it you know, it supports like many different chips. Yeah, and in the platform system interface project again, I'm actually collecting like a lot of information. So essentially what you see in this list here, and I'm going to expand that over time. So yeah, if you follow this link here to the section Maskroms loaders, you will find more over time. Yeah, so a rough conclusion. There are many different chips. They have different protocols. They are all different per vendor. And if you have the right tools, you can actually leverage the capabilities of your chip. So you can do like everything you want with them. The usually lowest common denominator is you can just load and run code. Okay. So our goal is to run our code as early as possible. And then if we want, we can provide our own interfaces again. That can be, for example, fast boot, or maybe you come up with something else at some point. And yeah, with that, we're at the end here. Thank you very much for listening. And yeah, if you have any questions, just raise your hands and ask them. I think we still have a few minutes. And otherwise, here's already all the references, also the link to the PDF file that is up here, and then the talk from last year. Thank you. Oh, oh.
Of like hidden instruction in expressive chips.
Ah, good one. Yeah.
Is it really like backdoor, or it's common for many chips and many providers?
Yep. It's a perfect question. Also funny because we have people from Expressive here. I actually wanted to have that in the presentation initially, and then thought, well, yeah, let's put it somewhere else. But yeah, let's answer the question, and let's recap the news to those who don't know. So recently, some security researchers said, hey, there is a backdoor in the Expressive chips. It allows me to run arbitrary code and execute that code. And they did not mention that that is not something that you can remotely execute, but it's only something for which you already need to have access to the system. So it's essentially just an interface as what I just showed here, and it also has these sorts of commands like you can read to the flash, you can write, you can read from the flash, you can write to the flash, you can query for some information and so on. I think they have like, I don't know, a good bunch of a dozen commands or something. So yeah, it's really not a backdoor, it's just the same interface that you would also get from every other chip for development, for provisioning and loading initial code. Yeah, thank you.
Thank you.
By the way, you can also find a statement on Expressive's own website. Yeah. Right, I guess that's it. Then, yeah, thank you very much again.